Due to the development of building constructions, high-density building areas are created, and it has become a crucial factor in understanding how microclimate dynamics act within those areas. In this research, wind interference and tunneling effects will be analyzed using CFD with varying building arrangements. Membrane-assisted electrocoagulation technology is an advanced hybrid wastewater treatment method that can use to remove microplastics from domestic wastewater. In this research, the optimum electrocoagulation reaction parameters were identified, and the fabrication of a microfiltration membrane was done for removal of microplastics. This research aims to identify the most cost-effective soil stabilizer between OPC and fly ash-based geopolymer for controlling surface heave in expansive soils, ensuring that flexible pavement heave is limited to acceptable levels while minimizing costs. CBR tests on raw and stabilized soil samples, followed by swell pressure tests, were conducted to assess the required subgrade stabilization depth. The final analysis compares the total construction costs to identify the more economical stabilizer. The Mid-Canal in Kandy is a highly polluted stream that flows into the main drinking water source of the city, Mahaweli River. To improve its water quality, the efficiency of the Greater Kandy Sewerage Project's collection system was assessed by measuring key parameters like pH, BOD5, fecal coliforms, and others across various locations during wet and dry periods. Despite ongoing efforts, the analysis revealed that the water quality of the Mid-Canal remains poor, as confirmed by the Water Quality Index developed through this research. Half-joint beams, known as dapped end beams, feature reduced depth at the beam's ends to facilitate support. The reinforcement corrosion at the N-ib area has affected the half-joint beam strength significantly. Due to that, several bridge collapses have been reported over the past few decades in several countries. The saltwater intrusion due to de-icing salts is the major source of corrosion. With the help of a non-linear finite element model, the behavior of the half-joint beams affected by corrosion has been investigated. This study investigates the effects of incorporating rice husk ash, RHA, into concrete mixtures, focusing on compressive strength, workability, and other key properties. The research explores how rice husk ash, an agricultural byproduct, can reduce the environmental impact of traditional concrete production to identify the optimal percentage of rice husk ash replacement in cement to enhance the compressibility and durability of concrete. Vertical subsurface flow, constructed wetlands, VSSF-CWs, are effective for wastewater treatment, but often face clogging issues that can reduce efficiency. To address this, backwashing was introduced to mitigate clogging and enhance system performance. This research evaluated the impact of backwashing on VSSF-CWs by analyzing key water quality parameters, including pH, BOD5, COD, fecal coliforms, and total suspended solids, before and after the interventions. Exploring a sustainable alternative to river sand, this research develops a fine aggregate blend using sea sand and manufactured sand. While sea sand is affordable, concerns about chloride contamination and inconsistent particle sizes arise. To offer an eco-friendly, reliable solution for construction, maintaining structural integrity without compromising quality, this study examines the mechanical and durability properties of the blend to ensure it matches the performance of river sand. The influence of particle shape on the shear strength of large granular materials used in civil engineering, such as breakwater structures and rock-fill dams, is examined in the study. Various particle shapes are simulated using the discrete element method, and numerical values, such as the elongation index, flatness index, and aspect ratio, are analyzed. Additionally, a Python-based artificial neural network model predicts the friction angle and void ratio, capturing the non-linear relationship between particle shape and shear strength. Right turns from minor roads onto divided highways at unsignalized T-intersections often pose serious accident risks. To address this problem, the study investigates key conflict points, including crossing and merging conflicts, to determine accident risk factors. By analyzing CCTV footage, the research developed an accident risk model, which considers factors like vehicle types, approach velocity, and traffic flow on the main road that correlates with post-encroachment time. Excessive bank erosion at river confluences with lateral inflow poses a significant challenge. To address this, the study investigates the impact of a strategically placed training levee to control flow and reduce erosion. Using both experimental and computational methods, including HECRA's 2D simulations, the research examines flow behavior under various conditions, with and without the levee. The model considers factors such as river curvature, lateral inflow, and the levee's role in flow redistribution, aiming to determine the optimal orientation for effective erosion mitigation. Bridges are critical components of infrastructure, but early structural failure is a frequent issue. This research addresses the problem by using a deep learning approach for damage detection. A finite element model of a bridge was developed, simulating real-world conditions with vehicle-induced responses. The core of the system includes 175 deep learning networks, reducing data requirements by 84% while maintaining precision. This method was tested on the Luella Bridge, showing promising results for long-term reliability. This study examines the shrinkage behavior of modified high-volume fly ash, HVFA, concrete modified by in-situ grown CSH, using slag as a sustainable alternative to conventional mixes. The research investigates how fly ash, slag content, curing, and environmental conditions impact compressive strength and shrinkage. The findings indicate that HVFA mixes with slag enhance early-age strength while keeping shrinkage within acceptable limits, and emphasize the need for optimized mix designs and shrinkage-reducing additives to improve performance. Earthquake-induced structural failures highlighted the importance of nonlinear analysis in reinforced concrete frame structures. This research introduces a simplified model to predict flexure-shear behavior in RC structures. Using OpenSees for flexural response and response 2000 for shear deformation, the model applies shear curves through springs or integration points. Validated by pushover and cyclic loading tests, model effectively predicts nonlinear performance and helps assess vulnerability to brittle failure. In addition to the detailed research showcased, many more studies are being conducted within the department that cannot be fully captured in this brief summary. Here are just a few examples. In materials and structural engineering, projects include structural health and performance monitoring, the use of ultra-high-performance fiber-reinforced concrete for structural rehabilitation, and the development of eco-friendly cement alternatives. In geotechnical and transportation engineering, researchers explore topics such as optimizing transportation systems and improving soil stabilization techniques. In fluid and environmental engineering, studies range from coastal conservation, disaster management, rainfall runoff and flood modeling, to assessing the environmental impact of urban water systems. These efforts highlight the diverse and impactful research taking place within the department.